Have you ever wondered what happens when your body can properly use its stored energy? That's what glycogen storage diseases are all about. When enzyme malfunction, energy becomes trapped. To explain this further, let us take you into the detailed journey on what glycogen is, how it is managed chemically inside the body, what happens when the system fails, and how these diseases affect real patients.
But before we begin, let me introduce myself. I'm Crochet Alonzo, and my group mates are Harry Adriano, Haven Agabin, Jomesti Pilar, and Shaira Ordas, and we're excited to share our work and insights with you today.
Picture a bustling city reliant on a vast warehouse where food supplies are stored and distributed with perfect timing. This warehouse employs specialized workers who carefully package, stockpile, and release food to feed the city through good times and bad. Now, imagine if some of these workers could not perform their tasks. Food starts to accumulate in the warehouse, unusable and piling higher, or worse, the city starves because the food isn't released when needed. This scenario mirrors our body's energy management system involving glycogen, a key energy storage molecule. Just like the warehouse workers, our body relies on enzymes to store glycogen safely and mobilize it efficiently for immediate energy needs. Problems occur when this enzyme malfunction due to inherited genetic mutation leading to glycogen storage diseases. Today, we'll zoom in on a detailed journey into what glycogen is, how it's managed chemically inside the body, what happens when the system fails, and how these diseases affect real patients. Through clinical examples and emerging treatments, we'll unravel the intricate biology behind these often overlooked disorders.
So, in discussing the biology and the importance of glycogen, the first step would be understanding what is glycogen and why our bodies depend so heavily on it. So, for starters, glycogen is a large branch polymer of glucose molecules functioning as the body's primary carbohydrate storage molecule. The liver and the skeletal muscles are the major storage depots, each serving distinct physiological roles. Liver glycogen acts as a glucose reservoir to maintain normal blood sugar levels, especially during fasting or between meals. Muscle glycogen, on the other hand, serves primarily as a direct energy source for muscle contractions during physical activity. This glycogen storage system is highly dynamic, controlled by a network of enzymes that synthesize and degrade glycogen based on the body's energy demands. Glycogen synthase is a critical enzyme for building the glycogen chain, while glycogen phosphorylase initiates its breakdown to release glucose 1-phosphate, which is then converted and used for energy production. Other enzymes such as the debranching enzyme also specialize roles in managing the complex branch structure of glycogen. The balance of glycogen metabolism is finely regulated by hormones like insulin and glucagon, which acts as signals governing energy storage and release. For example, after a meal in carbohydrates, insulin stimulates glycogen synthesis, encouraging the body to store glucose. Conversely, during fasting or exercise, glucagon and epinephrine trigger glycogen breakdown to maintain energy supply. Take this as an example. When you eat breakfast, your body converts some glucose from food into glycogen stored in the liver and muscles. Later, while at work or school, your body taps into these glycogen stores to keep your blood sugar stable and power your muscles during movement. Without a functioning glycogen system, this delicate energy supply chain breaks down.
So, what are glycogen storage diseases? Glycogen storage diseases are a group of inherited metabolic disorders characterized by defects in the enzyme regulating glycogen storage and usage. These enzyme deficiencies disrupt the normal balance, causing either excessive accumulation of abnormal glycogen or inability to mobilize stored glycogen when needed. This imbalance can cause serious problems in organs heavily reliant on glycogen, principally the liver and muscles. Glycogen storage diseases can be classified into multiple types, based on the specific enzyme affected and the primary tissue involved. For example is the type 1 glycogen storage disease, or also known as the von Wierka disease. It results from a deficiency of the enzyme glucose 6-phosphatase, which prevents the liver from releasing glucose into the blood. Patients often suffer from a severe hypoglycemia, enlarged liver or the hepatomegaly, and metabolic imbalances like high levels of lactic acid and uric acid. For example, a toddler named Liam often feels weak and dizzy, especially before meals. His parents notice that he needs to eat frequently even at night. To prevent low blood sugar, his belly looks swollen due to an enlarged liver. Liam's doctor explained he has type 1 GSD, meaning his liver can properly release glucose. Next is the type 2 disease, or also known as the Pompe disease. It is caused by a deficiency of lysosomal acid alpha-glucosidase, leading to glycogen buildup inside lysosomes, especially in muscle cells. This results in progressive muscle weakness and, in severe cases, heart enlargement and respiratory issues. For example, a baby shows signs of weakness and has trouble lifting her head. Doctors notice her heart is larger than normal. Over time, her muscles weaken further and she struggles to breathe without support. She is diagnosed with Pompe disease, showing how glycogen buildup can damage vital muscles. Next is the type 3 glycogen storage disease, or also known as Fori or Forbes disease. This form results from a missing the branching enzyme, which causes incomplete glycogen breakdown. It affects both the liver and muscles, leading to low sugar, enlarged liver, slow growth, and muscle weakness that may improve with age. For example, a 6-year-old girl tires easily during play and has a highly swollen belly. Her parents notice she's smaller compared to classmates. Tests reveal that she has type 3 GSD, and with a special high-protein diet, her energy and growth gradually improve. Next is the type 4 or the Andersen disease. This type happens when the branching enzyme is defective, creating abnormal glycogen that damages the liver and sometimes the heart or muscles. It leads to liver cirrhosis, failure, and often serious complications in early childhood. For example, a 3-year-old boy becomes easily tired and develops jaundice. His doctor finds his liver is scarred and enlarged. Genetic testing confirms type 4 GSD, where abnormal glycogen causes liver damage. This story shows the severe impact of enzyme defects on organ health. Next is the type 5 or the McArdle disease. It is caused by a defect in muscle glycogen phosphorylase. This type affects muscle glycogen breakdown during exercise. Patients experience muscle cramps, fatigue, and exercise intolerance, but liver functions remain normal. Like for example, a 16-year-old student athlete joined basketball practice but often feels his muscle cramp painfully after running short sprints. After several tests, doctors discover he has type 5 GSD. With proper management, Jake learns to warm up slowly and avoid overexertion.
Next, how glucose storage diseases affect the body and patient life. So, the clinical impact of glucose storage diseases depends on where the glycogen metabolism is impaired and how severely. In type 1 GSD, the liver's inability to release glucose results in life-threatening low blood sugar during fasting. This causes symptoms like lethargy, seizures, and developmental delays. The liver also enlarges due to glycogen buildup and fat accumulation, which can impair liver function over time. Living with type 1 GSD requires constant vigilance and strict dietary regimens. Parents often need to give their children cornstarch-containing meals or continuous nocturnal feeding to maintain blood sugar. This chronic burden illustrates the real-world challenges families face managing GSDs daily. Pompe disease, affecting muscle tissue, causes progressive muscle weakness beginning in infancy for severe forms of adulthood for milder presentations. Cardiomegaly, or enlarged heart from glycogen buildup in cardiac muscle, is a key complication. Patients often face breathing difficulties, motor delays, and require ventilatory support as disease progresses without treatment. Alternatively, McArdle disease manifests during adolescence or early adulthood with exercise intolerance. Patients experience muscle cramps, fatigue, and sometimes muscle breakdown or rhabdomyolysis after intense activity. This reduces quality of life and prompts lifestyle changes such as avoiding strenuous exercise and relying on alternative energy sources. These diseases offer clinical lessons on how a single enzymatic defect can cascade into systemic issues. For instance, glucose 6-phosphate deficiency not only leads to hypoglycemia but also lactic acidosis, hyperuricemia, and hyperlipidemia due to altered metabolism, showing the broad metabolic ripple effects.
Diagnosing glycogen storage diseases requires a combination of clinical suspicion, biochemical testing, and genetic analysis. Physicians start by evaluating symptoms such as hypoglycemia, hepatomegaly, or exercise intolerance. Blood tests reveal biochemical markers like low glucose, elevated lactate, or enzyme indicating muscle damage. Next, specialized enzyme activity assays on blood cells or tissue biopsies can confirm enzyme deficiencies. For example, liver or muscle biopsies stained for glycogen content reveal abnormal accumulations characteristic of GSDs. Genetic tests identify mutation in specific genes linked to different types of GSD. Molecular diagnosis is crucial not just for confirmation but for accurate subtype classification. This guides prognosis and management, especially now with enzyme replacement therapies available for some types. Furthermore, prenatal and newborn screening were available, help in early detection improving outcomes. A practical example comes from newborn screening program in some countries that identify Pompe disease early, allowing prompt initiation of enzyme replacement therapy before symptoms develop, dramatically improving survival and quality of life.
For treatment, management, and future directions of glycogen storage diseases or GSDs types 1 through 6 as classified by their respective enzyme deficiencies and tissue involvement. We begin with type 1 or von Gierke disease, which results from a deficiency of glucose 6-phosphate. Patients face severe hypoglycemia and metabolic disturbances due to impaired glucose release from the liver. The key management here is dietary control. Frequent high carbohydrate meals and raw cornstarch administration to maintain blood glucose levels and prevent hypoglycemic episodes. Additionally, pharmacologic treatments such as allopurinol are used to manage secondary complications like hyperuricemia. Importantly, ongoing research highlights promising future directions, including gene therapy and mRNA-based treatments aimed at correcting the underlying enzyme deficiency, which could substantially improve long-term outcomes. Moving on to type 2 or Pompe disease, which is caused by deficiency of lysosomal acid alpha-glucosidase. This form primarily affects muscle cells with progressive weakness and cardiopulmonary complications. In this case, enzyme replacement therapy has become the standard treatment, significantly improving muscle function and respiratory health. Supportive therapies, including physical therapy and respiratory support, are crucial. Looking ahead, gene therapy and novel enzyme formulations are under active investigations to enhance therapeutic effectiveness and reduce immune response risks. Next, type 3, known as Cori or Forbes disease, which stems from a lack of the branching enzyme impacting both liver and muscle tissue. Similar to type 1, dietary management with frequent meals and cornstarch is essential to control hypoglycemia. Although no curative treatment exists yet, clinical monitoring of liver function and muscle symptoms is vital. Current research efforts focus on metabolic and genetic therapies to improve glycogen degradation and prevent liver damage. Regarding type 4 or Andersen disease, the deficiency of the branching enzyme leads to the accumulation of abnormal glycogen releasing. Regarding type 4 or Andersen disease, the deficiency of the branching enzyme leads to the accumulation of abnormal glycogen, causing progressive liver disease. Unfortunately, there is no specific treatment to halt disease progression, and management concentrates on supportive care, including liver transplantation in cases of liver failure. Future therapeutic options remain underexplored, but advances in gene therapy may offer hope. Turning to type 5 or McArdle disease, characterized by defective muscle glycogen phosphorylase. The treatment approach emphasizes lifestyle modifications. Patients must avoid strenuous exercise that precipitates muscle cramps and fatigue while maintaining nutritional support for energy metabolism. Although no cure is available, research into gene therapy and metabolic agents continue to evolve. In summary, the current management of GSDs largely relies on dietary control and enzyme replacement where applicable, while emerging therapies in gene editing and molecular medicine hold promise for the future. Continued research and clinical trials are essential to bring these advances into routine care. So to wrap up, glycogen storage disease highlights the critical role of enzyme deficiencies in disrupting normal glycogen metabolism and their clinical implications. Understanding these disorders sets a strong foundation for exploring other essential metabolic pathways. Next, we will delve into the hexose monophosphate shunt pathway, also known as the pentose phosphate pathway, which plays a vital role in cellular metabolism by generating NADPH and ribose 5-phosphate. This will be discussed by our remaining groupmates, so stay tuned in for detailed explanations on how this pathway supports anabolic reactions and cellular defense mechanisms against oxidative stress. Stay engaged as they break down the biochemical steps and highlight its clinical significance.
Hello guys, now we move on to our topic 2, a hexose monophosphate shunt pathway. The hexose monophosphate shunt, also known as the pentose phosphate pathway. The HMP shunt is an alternative pathway to glycolysis and is used to produce ribose 5-phosphate and nicotinamide adenine dinucleotide phosphate or NDA-PH. This pathway occurs in the oxidative and non-oxidative phases, each comprising series of reactions. Furthermore, HMP shunts takes place in the cytoplasm. A 6-carbon sugar glucose or glucose 6-phosphate may enter the glycolytic pathway or HMP shunt As what I have said, that the HMP shunt is an alternative pathway to a glycolysis. Depending on the cell's individual needs at that time, once the glucose enters the HMP shunt, it undergoes a series of reactions broken into the oxidative or irreversible and non-oxidative phase or reversible phases.
Now let's move on to the HMP shunt pathway, the alternative pathway to glycolysis and Krebs cycle for oxidation of glucose. So why is it considered to be an alternative pathway? Take for instance the process of glycolysis, where glucose will convert to glucose 6-phosphate then be converted to pyruvate. However, through HMP shunt, glucose 6-phosphate can leave glycolysis and enter HMP shunt. Now that glucose 6-phosphate entered the HMP shunt, it will be converted to glucose 6-phosphogluconolactone through the enzyme glucose 6-phosphate dehydrogenase, which will reduce NADP to NADPH. Then this glucose 6-phosphogluconolactone be converted to glucose 6-phosphogluconate through the enzyme gluconolactonase, which will reduce H2O to hydrogen ion. Furthermore, glucose 6-phosphogluconate be converted to ribulose 5-phosphate through the enzyme glucose 6-phosphogluconate dehydrogenase, which will reduce NADP to NADPH. As you can see, from 6 carbon, it turns to 5 carbons. That means there's a decarboxylation that occurs and carbon dioxide release. Now from ribulose 5-phosphate, it will be converted into 2, which is the ribose 5-phosphate through the enzyme ribulose 5-phosphate isomerase and cellulose 5-phosphate through the enzyme ribulose 5-phosphate 3 epimerase. Now the ribose 5-phosphate will transfer 2 carbons to cellulose 5-phosphate. With that, glyceraldehyde 3-phosphate will produce, and upon accepting the 2 carbons, the cellulose 5-phosphate will be converted to pseudoheptulose 7-phosphate via this enzyme, which is the transketolase. Transketolase transfer 2 carbon units between sugar. So from 5 it turns to 3, and then 5 it turns to 7. Similarly, glyceraldehyde 3-phosphate will be converted to fructose 6-phosphate upon accepting the carbon, and pseudoheptulose 7-phosphate will be converted to erythrose 4-phosphate upon transferring its 3 carbon molecules. So from 7, it turns to 4 through the help of enzyme transaldolase. The only difference between transaldolase and transketolase is the number of carbon they transfer. Transaldolase transfers 3 carbon units, while transketolase transfers 2 carbon units. Then if needed, the fructose 6-phosphate will be part of glycolysis. Again, cellulose 5-phosphate will transfer 2 carbons to erythrose 4-phosphate via transketolase enzyme. Hence, glyceraldehyde 3-phosphate and fructose 6-phosphate will produce. And if needed, these two will be part of glycolysis. And that is HMP shunt pathway.
The clinical significance and deficiencies of the hexose monophosphate shunt pathway. Interruptions in the hexose monophosphate shunt can have effects on an individual. What can arise is the deficiency of the enzyme called glucose 6-phosphate dehydrogenase, the enzyme required to produce NADPH or nicotinamide adenine dinucleotide phosphate, in the initial step of the HMP shunt, which protects cells from oxidative damage. Red blood cells depend heavily on this pathway. Red blood cells become defenseless against harmful substances, and since red blood cells carry oxygen, which is a natural oxidizer, they are constantly exposed to oxidative stress. And as a result, they break easily, leading to hemolytic anemia, a condition where red blood cells are destroyed faster than the body can replace them. One of the most common disorders involving this pathway is the deficiency of the enzyme called glucose-6-phosphate dehydrogenase. This enzyme is responsible for starting the hexose monophosphate shunt pathway. The deficiency is inherited through the X-linked recessive disorder, most commonly seen in African Americans. When this enzyme is lacking, the body fails to produce enough reduced nicotinamide adenine dinucleotide phosphate, which leaves the red blood cells extremely sensitive to oxidizing agents. Once a person with this deficiency is exposed to certain triggers, the deficiency can lead to hemolytic anemia. Oxidative stress can come from infections, chemical exposures to medications, or certain foods. Several everyday substances that can trigger red blood cell destruction in people with this enzyme deficiency is fava beans, which contains natural compounds such as vicin, divicin, convicin, and isouromyl, all of which create a strong oxidants in the body. In affected individuals, eating even a small amount of fava beans can lead to severe hemolysis. Another trigger is nitrofurantoin, an antibiotic commonly used to treat urinary tract infections. Nitrofurantoin suggests it is less likely to cause oxidant hemolysis in individuals with glucose-6-phosphate dehydrogenase deficiency. Another is the anti-malarial medicines that can also cause hemolysis in affected individuals. Aside from the red blood cell disorders, the hexose monophosphate shunt can also play an important role in diagnosing vitamin B1 deficiency. Vitamin B1 or thiamine is needed by several enzymes that help the body convert glucose into usable energy. When a person is deficient in vitamin B1, a wide range of health problems can appear. One serious condition is the Wernicke-Korsakoff syndrome, which is a brain and memory disorder that requires immediate treatment. Wernicke-Korsakoff can have risk factors like inflammatory bowel diseases, heart failures, and even kidney failures. Vitamin B1 deficiency can also lead to beriberi, which has two forms. In wet beriberi, it can result in cardiac failure and dilated cardiomyopathy. In dry beriberi, the nerves are affected, leading to numbness, muscle weakness, and eventual paralysis if untreated. These complications can become fatal, so it is important to detect the deficiency promptly. The connection between vitamin B1 or the thiamine deficiency and the hexose monophosphate shunt lies in an enzyme called transketolase. This enzyme depends on vitamin B1 to function normally. To diagnose a suspected deficiency, healthcare providers measure transketolase activity in red blood cells before and after giving vitamin B1. If the enzyme activity increases after supplementation, it confirms the deficiency. This is important because early detection prevents serious complications, especially neurological and cardiac damage. For treatment, when treating vitamin B1 deficiency, the treatment usually includes giving both thiamine and dextrose, since thiamine deficiency causes impaired glucose breakdown.
In conclusion, the pentose phosphate pathway converts glucose-6-phosphate to ribose-5-phosphate, which is needed for the synthesis of DNA and RNA, and thus have an effect in our body. In addition, ribose-5-phosphate can also return to glycolysis as needed, and NADPH is produced as a result of these reactions. Now, glucuronic acid pathway is our last topic. So what is it all about?
Now, let's move on to our next topic, which is the glucuronic acid pathway. So, what is the glucuronic acid pathway? The glucuronic acid pathway is also known as the uronic acid pathway. It is a minor but important route in glucose metabolism. It converts glucose into glucuronic acid through a series of enzymatic steps. This pathway is crucial because it helps detoxify various substances such as drugs and toxins by transforming them into more water-soluble compounds that can be easily excreted from the body. Besides detoxification, the pathway also plays a key role in the biosynthesis of vital molecules, like glycosaminoglycans, which are essential components of connective tissues, cartilage, and synovial fluid. In certain animals, this pathway even contributes to the production of vitamin C. The process begins with the glucose being converted into glucose 6-phosphate, then to UDP glucuronic acid, which acts as a precursor for multiple biochemical reactions in the body. The glucose acid pathway supports both metabolic detoxification and the synthesis of important biomolecules that maintain our physiological functions.
Before we proceed to the glucuronic acid pathway, let's first discuss how glucose is converted to glucuronic acid. The first step is phosphorylation, where glucose is converted to glucose 6-phosphate by the enzyme hexokinase or glucokinase.
This reaction consumes ATP and effectively traps the glucose within the cell. This is followed by isomerization, or a phosphate shift. It is catalyzed by phosphoglucomutase, which moves the phosphate group from carbon 6 to carbon 1 yielding glucose 1-phosphate. Next is the activation step. It is essential for making the sugar a high-energy donor. UDP glucose pyrophosphorylase catalyzes the reaction between G1P and UTP to form the activated compound UDP glucose. The final stage is oxidation. It is carried out by the enzyme UDP glucose dehydrogenase. This enzyme oxidizes the carbon 6 primary alcohol group of UDP glucose into a carboxyl group. This oxidation requires 2 molecules of NAD per cycle, which are reduced to NADH. The final active product of this initial pathway is UDP glucuronic acid. The resulting glucuronic acid structure is characterized by the carboxyl group of carbon 6 instead of the primary alcohol group found in glucose. It is vital for major body functions, including the detoxification process known as glucuronidation and the biosynthesis of structural molecules like proteoglycans. So let's proceed to glucuronic acid pathway. It is responsible for converting glucose into glucuronic acid. It is an important substance for detoxification and the formation of structural molecules in the body. Unlike the hexose monophosphate shunt, the glucuronic pathway does not directly generate ATP through substrate-level phosphorylation, but it does produce NADH, which can be used for ATP synthesis via mitochondrial oxidative phosphorylation. As you can see in this diagram, it is an alternative route for glucose metabolism. The glucuronic acid pathway, it starts with glucose 6-phosphate. Ito yung unang step natin, which is the enzyme phosphoglucomutase then rearranges it into glucose 1-phosphate. Next, the glucose 1-phosphate reacts with UTP or the uridine triphosphate. The enzyme UDP glucose pyrophosphorylase catalyzes the formation of UDP glucose, releasing PPI or the inorganic pyrophosphate. So dito nagkakaroon na tayo ng UDP glucose. Now, the UDP glucose undergoes oxidation. The enzyme UDP glucose dehydrogenase and converts it to UDP glucuronate. This step requires 2 NAD, which is reduced to 2 NADH plus hydrogen. So dito may energy naman na natatransfer. So, the UDP glucuronate is then hydrolyzed. The enzyme glucuronidase catalyzes the reaction, releasing UDP and forming D-glucuronate. So, dito parang tinanggal na natin yung UDP. Next is the D-glucuronate is reduced to L-gluconate. This step requires an NADPH plus hydrogen, which is oxidized to NADP. Okay, so L-gluconate has two possible fates. On one path, it can be oxidized to 3-keto-L-gluconate. This step requires NAD plus, which is reduced to NADH plus hydrogen. Then 3-keto-L-gluconate spontaneously decarboxylates, losing carbon dioxide to form L-cellulose. On the other path, L-gluconate can be dehydrated, losing hydrogen to form L-gulonolactone. Now let's follow the L-cellulose pathway. The L-cellulose is reduced to xylitol. The enzyme xylitol dehydrogenase catalyzes this reaction. This step requires NADPH plus hydrogen, which is oxidized to NADP. Interestingly, a deficiency in xylitol dehydrogenase can lead to idiopathic pentosuria in humans, where L-cellulose accumulates in urine. Next, xylitol is oxidized to D-cellulose, requiring an NAD, which is reduced to an NADH plus hydrogen. D-cellulose is then converted to cellulose 5-phosphate, which enters the hexose monophosphate shunt. Now let's talk about the vitamin C. In animals that have the necessary enzymes, L-gulonolactone can be oxidized to 2-keto-L-gulonolactone, which is then converted to L-ascorbic acid or vitamin C. But this enzyme gulonolactone oxidase is absent in primates including humans, kaya hindi tayo makagawa ng sarili nating vitamin C. So, dito nag-e-end yung glucuronate pathway, which is important for detoxification.
The glucuronic acid do have functions or roles such as in detoxification and conjugation reactions and different syntheses. Firstly, its role in detoxification and conjugation reaction. Glucuronic acid is involved in the detoxification of compounds such as drugs. That means it is essential for removing unwanted substances from the body and undergo glucuronidation. Glucuronidation means a metabolic process that makes substances like drugs, toxins, and hormones more water-soluble by attaching a glucuronic acid molecule via the enzymatic action of UDP glucuronosyl transferase, and the product that is being transformed or processed as water-soluble compound is called glucuronides, and these glucuronides are then easily excreted from the body through bile and urine. To simply understand, here's an analogy. Take for instance doing skincare. So you want to remove your pimple, which is the unwanted compound. Now you have applied cleanser, toner, serum, moisturizer, and etc. A skincare process. So that is what we call glucuronidation. Now you have applied a pimple patch. That is considered to be the enzyme UDP glucuronosyl transferase. And when your pimple gets dried, it is what we call the glucuronides.
To delve deeper into glucuronic acid pathway, we will now be focusing particularly on its critical roles in glycosaminoglycan synthesis and vitamin C production. To begin with glycosaminoglycan synthesis, this process starts with the activation of sugar precursors in the cytoplasm, notably UDP glucuronic acid, which is a key activated form of glucuronic acid. These UDP sugars are transported into Golgi apparatus, where the biosynthesis of glycosaminoglycans takes place. GAGs are long, linear polysaccharides composed of repeating disaccharides units, one of which often includes glucuronic acid. These polysaccharides attach covalently to core proteins, forming proteoglycans, which are important molecules in the extracellular matrix that provide structural support to tissues such as cartilage, skin, and blood vessels. The initiation of GAG synthesis involves the attachment of a xylose molecule from the UDP xylose to specific serine residues on core proteins, creating a linker tetrasaccharide. Sequential addition of 2 galactose residues, and finally, a glucuronic acid residue follows, forming a fundamental tetrasaccharide linker that primes the polymerization of the GAG chain. Depending on the tissue formation, different types of GAGs such as chondroitin sulfate or heparan sulfate are formed by adding specific sugar units and undergoing modifications like sulfation and epimerization to diversify function. This modular synthesis resembles building with Lego blocks, where each sugar addition changes the structure properties and biological roles. Importantly, the negative charges introduced by sulfation and the presence of glucuronic acid confer hydrophilicity and the ability to bind water, making GAGs essential for maintaining tissue hydration, elasticity, and resilience to compression. For example, in cartilage, a grecan, a proteoglycan rich in chondroitin sulfate, provides cushioning by attracting water molecules. Additionally, GAGs play roles in cell signaling, molecular recognition, and coagulation. Dysfunction in GAG synthesis or degradation is implicated in diseases such as mucopolysaccharidosis and osteoarthritis. Switching now to vitamin C synthesis, in most mammals, glucuronic acid serves as a precursor. Through a series of enzymatic reactions, starting with the conversion of UDP glucuronic acid to L-gluconate and eventually to L-ascorbate or vitamin C. The pathway enables endogenous vitamin C production. This vitamin acts as a potent antioxidant, protecting cells from oxidative damage and as a cofactor for hydroxylation enzymes critical in collagen synthesis, necessary for wound healing and connective tissue integrity. An analogy here is that glucuronic acid is the raw material, and vitamin C is a finished product essential for building and repairing the body's infrastructure. However, humans along with some primates and guinea pigs have lost the ability to synthesize vitamin C due to inactivation of the enzyme L-gulonolactone oxidase, the final step in the pathway. As a result, vitamin C becomes an essential nutrient, requiring dietary intake from fruits and vegetables. This evolutionary loss underscores the pathway's importance and the physiological necessity of vitamin C, evident in diseases like scurvy caused by its deficiency. In closing, the glucuronic acid pathway is vital for structural and signaling roles in tissues, and vitamin C, which is indispensable for antioxidant defense and collagen formation. Understanding this mechanism provides insight into fundamental biology and potential therapeutic targets for related pathologies.
The significance of uronic acid pathway or glucuronic acid pathway. Glucuronic acid pathway is an alternative route for glucose metabolism, and its main importance lies in producing UDP glucose and UDP glucuronic acid. UDP glucose is needed for glycogen storage, galactose metabolism, and lactose synthesis. It also serves as the precursor for UDP glucuronic acid. UDP glucuronic acid plays a major role in detoxifying substances in the liver, including bilirubin, steroid hormones, and drugs. It is also essential for the formation of glycosaminoglycans such as hyaluronic acid, heparin, and for producing L-iduronic acid, which is found in important structural molecules like dermatan sulfate and heparan sulfate, both of which contribute to the structure and elasticity of the skin, blood vessels, and other tissues. The disorder of the glucuronic acid pathway. One example of disorder linked to this pathway is essential pentosuria. Essential pentosuria is a rare, inherited metabolic condition caused by a deficiency of the enzyme xylitol dehydrogenase and sometimes cellulose reductase. These enzymes are responsible for converting L-cellulose into xylitol. When they are defective or absent, the L-cellulose accumulates and is excreted in large amounts through the urine. This condition follows as an autosomal recessive pattern, meaning a person must inherit the defective gene from both parents. L-cellulose in the urine can cause a positive Benedict's test, which is the same result seen in diabetes. People with this essential pentosuria have no symptoms and normal life expectancy, making the condition clinically benign.
To wrap up our three topics, glycogen storage disease, the hexose monophosphate shunt, and the glucuronic acid pathway are all essential metabolic routes that contribute significantly to energy management, cellular protection, and the synthesis of critical biomolecules within the human body. Glycogen storage diseases highlight the importance of proper glycogen metabolism, where enzyme deficiencies can lead to energy imbalances and organ dysfunction. The hexose monophosphate shunt emphasizes the production of NADPH, crucial for defending cells against oxidative damage, particularly in the red blood cells, and its connection to vitamin B1 metabolism. And the glucuronic acid pathway demonstrates its role in detoxification, facilitating the removal of harmful substances, and its involvement in the synthesis of the glycosaminoglycans. It is vital for tissue structure and function. Understanding these interconnected pathways is crucial for comprehending the complex biochemical processes that sustain life and for developing effective strategies to address related disorders. So that's it for our look into glycogen storage disease, the hexose monophosphate shunt, and the glucuronic acid pathway. We hope we've helped you understand how these important things work in our body. Thanks for learning with us. We hope you pick up something new.